Hey class, welcome back. We are taking a look at probability, page P14, looking at independence. This is the last part that we're going to look at before we get into solving some little more complex problems here. So, independence. Two events A and B are independent if the occurrence or non-occurrence of either event cannot influence the occurrence or the non-occurrence of the other event. If they are independent, the following is true: that the probability of A given B is simply equal to the probability of A. And also the opposite, the probability of B given A is equal to the probability of B, and the probability of A and B is equal to the product of the two marginal probabilities. What does that mean? Well, let me give you an example here. So suppose the examples are the A is going to be flip a coin, and then B is going to be roll a die. And we're going to do those at the same time here. Now, the probability of getting ahead, given that we got a 1 when we rolled the die, is just the probability of getting ahead. In other words, it doesn't matter what you got on the coin, or on the die, it doesn't affect what you get on the coin. Who cares, in other words, right? The opposite is also true. That is, the probability of getting a 1, given that you got ahead when you flipped a coin, is just simply the probability of getting a 1 when you roll a die. So they don't affect each other in any way. Coming up with real-world examples is a little more complex in terms of that. You can take a look here at what's the probability that I wear a tie tomorrow versus whether it rains in Nova Scotia tomorrow. Those would be independent because one does not affect the other. You have to be really careful about that kind of thing, though, because it could be that I have a real interest here in Nova Scotia, and I always tend to wear a tie on days when it rains. So it doesn't necessarily mean that those two are independent. It's likely that they're independent, and I'll tell you that they are independent. I don't really care whether it's raining or not in Nova Scotia in terms of what I wear today or tomorrow. And by the way, the probability of me wearing a tie is pretty close to 0 right now anyways. So that is the way that works. And an interesting thing when we get into looking at correlation in Business 307 is two events that you would think are independent of each other, but actually looks like they're really related, and that is the birth rate of penguins in the Antarctic and the murder rate in Chicago. And it turns out actually that they're really highly correlated. And I think we talked a little bit about this before when we talked about spurious correlations here. But what we have here then is they're actually connected to another variable. In stats, we call it a lurking variable, and that's the weather. So when you've got an El Nino condition in the world here, you tend to get hotter temperatures in both places, and so the birth rate of penguins goes up because they're more mobile, they're more frisky. But you also have people who are hot and grumpy and on the streets at night in Chicago, and so the murder rate tends to go up too. And so they're actually connected to the weather. So those statistically are not independent of each other, even though practically you would say that one does not affect the other. So we're not necessarily talking about causation here, but about statistical dependency or independence. An important thing to note here is that people often confuse independence with events that are mutually exclusive. And so mutually exclusive events are completely dependent on each other. In other words, if I roll a die and I get a 2, it doesn't mean that it's independent of getting a 1, 2, 3, 4, 1, 2, 4, 5, or 6 on the same roll. It means if I got a 3, I didn't get any of the others, so they're actually completely dependent. What is independent is what I get in one roll versus what I get on the second roll, assuming that the way I pick up the die doesn't affect it in any way. So rolls on 2 dice. Let's put it down that way. So what I get on one dice doesn't affect what I get on the second dice or the second roll of the same die. Okay? And the same with flipping coins and so on like that. Just a point about that is that when people flip coins, they look at this and say, hey, I got 9 heads in a row. The next has got to be a head, or it's got to be a tail if I got 9 heads in a row, because there's no way I'm going to get 10 in a row. But actually, there's no memory when you're talking about flipping coins, unless, of course, it's the way that you pick up the coin and the way that you flip it. But assuming that that doesn't enter into it, maybe you've got 10 different people flipping coins and all that kind of thing, or you've got some fancy flipping machine or something, then they don't affect each other. Even if you end up with 9 heads in a row, the probability of getting the next coin being a head actually is still 50-50, right? So let's take a look here at number 10. A group of 300 persons is studied. 2 pieces of information is determined about them: the person's gender and their eye color. In this case, we'll simply use whether they have blue eyes or not blue eyes, recognizing that there's lots of other different eye colors, as well as different ways that people tend to identify their genders, but we'll keep it to the simple example here. So the question is the person's eye color dependent on his or her gender? Practically, we know that they are not related. They are independent. That's just from statistical studies. There's not a greater propensity for you to have blue eyes if you're a male versus being female, or vice versa. But let's take a look at the formulas at the top here. So let's take a look then at the probability that a person is male, given that they have blue eyes. Let me rewrite that. And I'll change colors here too. What's the probability that a person is male given that they have blue eyes? So I'm going to take a look at this first cell right here. That should be equal to, if they're independent, simply the probability that a person is male. Okay, let's add up some numbers here. Actually, I didn't leave a lot of room, did I? But let's add these up here and say that we've got 100 males, we've got 200 females, and so that's 300 in total. Then we've got 75 blue eyes and 225 not blue. They add up to 300. Okay, probability that of M and blue is equal to the probability of M given blue. Conditional probability is equal to the probability of M and blue divided by the probability of blue. And that's equal to M and blue is 25. It's actually 25 out of 300, of course. And blue is 75 out of 300. So that is 1/3. And that happens to be the probability that the person is a male. Probability of being a male is just 100 over 300. In other words, what we're saying here is that this ratio here of the 25 over 75 is the same as this ratio of 100 over 300. Okay, let's try another one. The opposite should be true as well. Probability of B given M is equal to the probability of B. If you take a look at these formulas up here. So, probability that a person is got blue eyes and is male divided by probability of male is going to be 25 over 100, which is a quarter. And that turns out to be actually the probability that a person is got blue eyes. Blue eyes is 75 out of 300. which is a quarter. So in other words, this ratio, 25 over 100, is the same as this ratio of 75 over 300. And then the last example here is, let's change this to maybe a purple, the probability of B and M, if they're independent, should be equal to the probability of B times the probability of M. So probability of B and M is going to be this guy here, 25 out of 300. And that should be equal to, and what you do is you just simply take the intersection of the two gives you your marginals. So the probability of B is 75 out of 300. And the probability of M is 100 over 300. 100 over 300 is a third. A third of 75 is 25. So you can get out your calculator and try this out, but you'll find out that works. By the way, it's important that you need to do that for every cell. So we've only looked at the first cell, which is the B and the M. It is true that if you have a 2 by 2 matrix, as soon as it works for one cell, the rest are all locked in. But if I had a 2 by 3 matrix or a 3 by 3 or anything bigger than a 2 by 2, you actually have to check all of the different cells there. Suppose one card is drawn from a deck of 52 cards. Are the events ace and spade independent of each other? That is, does knowing that a card is an ace have any bearing on the likelihood that the card is also a spade? So what I'd like you to do is give that a try. I'm going to take it up in just a second, but remember we took a look here at the cards. This is back on page, what is that, P10 down here. So this is how the cards are set up. If you're not familiar with the deck, P10. And now give that one a try. I'm going to assume that you've done that. So let's take a look at three statements then. So we're talking about ace and spade. So the probability of it being an ace, given that it's a spade, should be equal to the probability that it's equal to an ace. That's that first axiom right here. I'm using an S instead of a B in this particular case. So that's equal to, let's take a look at our formula for conditional probabilities. A and S over the probability of S would be 1 out of 52 cards are aces and spades, and then the number of spades are 13 out of 52. So it's equal to 1 out of 13. Probability that a card is an ace is 4 out of 52. There's 4 aces out of 52. So these two are equal. 4 out of 52 is equal to 1 out of 13. All right, let's try the opposite. Probability of S given A. If they are independent, should be equal to the probability of S. So that's the second one up here, where I'm using S instead of B. Probability of S and A, given A, is S and A, or the probability of, what goes in the denominator? A. So S and A is, we've already determined that to be 1 out of 52. There's one card which is both a spade and an ace, the ace of spades. And then the number of aces in the deck are 4 out of 52. So 1/4. That's equal to the number of spades. The probability that a card is a spade is 13 out of 52, and those are equal. So 1/4 of the cards are spades. Let's look at the last one here. And in this one, we're going to say the probability of ace and spade is equal to the probability of ace times the probability of spade. So I'm using this one here, where again I'm using S instead of B. All right, 1 out of 52, because there's one card which is an ace and a spade, is equal to probability that a card is an ace is 1 out of 13, or 4 out of 52. And the probability that a card is a spade is a quarter, or 13 out of 52. So if you multiply those out, you'll get 1 out of 52 is equal to 1 out of 52. Now, by the way, when you're proving independence, you don't have to do all three of these. You only have to do one of these. So I usually do this one. I think it's easier, but depending on if you've got the other numbers, you can do that. As mentioned before, when you're showing that two events are independent in terms of gender and eye color, like up here at the top, then you do need to do that for every cell, but I would probably just use this formula here. So I do that for the first cell, the upper left, blue and male, and then I move on to blue and not blue, the next one, and then blue and female, and then blue and not female. So you have to do that for all four, but you don't have to use all three methods. You can use any of the three methods here, but you'd have to do it for all four cells in that particular case. Some special notes to note. Unless it's already known that the events A and B are independent, if you're told that, then that's fine. Otherwise, it's important to use the more general formulas. So in the example that I used here, the probability of A given B is, I actually went through this calculation here in each case to show that it's equal to the marginal probability. So you don't jump straight there. You actually have to show it mathematically. Same down here then, okay? And consider the eye color above, so that we've actually just talked about this here, is that you need to show that independence holds for all four cells here. Now, as I mentioned, in a 2 by 2 matrix, if one of them turns out to be independent, it kind of locks in all the rest there. You can try that mathematically and so on, but it is possible to encounter a problem where one of these relationships exists, but not the others. So let me give you an example here. And so here's where we've got a 3 by 3 matrix. And let's take a look at this first cell right here. And what we've got here then is, if these are independent, then the probability of being Canadian and having blue eyes is equal to the probability of being Canadian times the probability of having blue eyes. So I'm just using that third statement from up here, right? This one right here. And I'm just checking that out here in this contingency table. So in other words, what I do is I take the two marginals here, and recognizing that these are all out of 20, pardon me, like that. Those are the, it's all out of 20 here. So the marginal probability is 2 out of 20. If they're independent, should be equal to, probability of being Canadian is 10 out of 20 times the probability of having blue eyes, which is 4 out of 20. Well, 10 out of 20 is a half, so half of 4 out of 20 is 2 out of 20. And so you're good. So you could look at this and say, yeah, it seems that this table shows independence, because that works, but it doesn't work for all the other cells. What's an obvious example here where it doesn't work? Let's take a look at it. See if you can figure it out. Well, this one here, or the one below it. And so the probability then of being Japanese and having green eyes, if they're independent, should be equal to the probability of being Japanese times the probability of green eyes. Here we've got 0 is not equal to 6 out of 20 times 2 out of 20. Okay, so if we took the marginals and multiplied them, remembering that they're all out of 20, 6 out of 20 times 2 out of 20 is not equal to 0. So what we have here then is that eye color overall is not independent of where you're from. Oh, your country of origin here, the color of your eyes. So they're not independent because we found an example where this does not hold. It has to hold for the whole table. All right, that leaves us with some interesting problems here. And so I'm going to stop the video at this point here, and then I'm going to work through a couple of these problems. I'm going to leave the other couple of problems for us to work through in class. So let's start.